Hey guys, so in this video we will be talking about atomic spectra, and this is a very important experimental result in quantum mechanics that will really shape how we look at quantum mechanics, and also shape some of the earlier versions of quantum mechanics such as Bohr's model of the atom. So let's look at what these results are. So essentially what we have in this experiment is we take a gas, and so in this first one we have a hydrogen gas, and this next one we have an iron gas, which is very hot. And what happens is when you run some heat or electricity, or you just really run energy through a gas, through any kind of gas, what it will do is it will actually start to release light. And you can actually break down exactly what colors of light it releases. And one might think that, oh, we'll just, release white light, just all the different colors, but that's not true. In fact, it will release very specific frequencies which correspond to the colors of light, right? And so for hydrogen, it's very simple. For iron, it's not quite as simple, but you can still see that there are definitely discrete lines, and these are called spectral lines. And so before we can really talk about what's happening and how scientists interpreted this, the first thing we have to talk about is what light is in general. And I'm not doing everything in this section quite in chronological order. I'm trying to connect these experiments thematically, which means I'll have to sort of tell you what we knew about light at this point in time, especially when we were really interpreting this. And we will see later in the photoelectric effect will really show everything we know about light and show why we know it from the photoelectric effect and the double slit experiment. So the first thing is light is a wave. Light has wave properties, it does things that waves do, and it has a wavelength and a frequency. And the frequency of light corresponds to the energy. So for light, let's put this in a yellow here. So for light, it's a wave, and the frequency corresponds to energy. And it also corresponds to color. Okay, so the frequency corresponds to both color and energy. And so what that would mean is we have different colors of light having different energies, right? So all three of these quantities are related is essentially what I'm trying to say here. So if you have different colors of light, that just means we have different energies of light. But while light is a wave, it also has properties of a particle, right? And this is called the wave-particle duality, and we will talk a lot more about this again with the photoelectric effect and the double slit experiment. But right now, all you have to do is just take that light has frequency, so it's like a wave where its frequency corresponds to its energy and also its color, and it also is a discrete particle, and it's called a photon. It's the particle of light, the photon. And a photon has a particle, but it has a frequency, and that frequency corresponds to its energy or what color of light. And it's actually not just color that it's associated with, but that light is called electromagnetic radiation. And so color is one of the things it can be represented by, but there are other types of radiation such as radio waves, microwaves, infrared, visible light. Then there's ultraviolet light, X-rays, and gamma rays. And so those are the different types, and I'll have a link in the description about electromagnetic radiation if you want to learn more about it. That's not really what we'll be talking about in quantum mechanics, but it's just important to know that there are a bunch of different things, different properties of light with different energy, right? And so in a certain range of energy, the light is represented, can be seen as color. And that's really what we're focusing on, especially in this experiment. Okay, so hopefully that makes sense. We've got a photon of light, which is a particle, but it's also like a wave, and it has a frequency, and that frequency corresponds to its energy. It also, for certain frequencies, corresponds to its color. Okay, and so now let's look at how we interpret these spectral lines, because this is very, very important. So the big idea here is what's happening to the electrons, right? The nucleus is, pretty much still. What's really moving around are the electrons. So we have electrons in a gas, And the electrons will then absorb energy. So we run energy through it. So this absorbs energy. Okay, and then it becomes a energetic electron, like that. And now you can sort of think about it. This is how a lot of teachers will explain it, where if you are really energetic and you're jumping around, that's not going to last. You're eventually you're going to sort of calm down and return back to your non-energetic state, which is called the ground state. And that's exactly what electrons do. They're not very stable when they have a high energy, and what that's going to mean is they're going to go back to being low energy. But the energy has to go somewhere. Energy can't just go away. That's the conservation of energy. And so what happens is the electron is going to release light, a photon of light, as it goes back down to the energy, to the lower energy. And this photon of light is what is released by the atom, right? It's released by the electron, and then we can see what kind of light is released. Now, if the energies of the electrons were random, they could be any energy, well, they could release any energy of photons, so we would just see a continuous, spectrum of light. We'd just see white light coming out, but that's not true. Only certain energies of light are released, which means only certain energy transitions are allowed in the electron. The electron can't jump from any energy to any energy. There are specific energies that the electron can jump from. That's what these discrete lines tell us. Now, why are there more for iron? Well, these are neutral gases, and neutral hydrogen has one electron, which makes it pretty simple. There are a certain amount of energies, and that electron can go between energies. For iron, there are a lot of electrons and a lot more energies for all of those electrons, and we'll talk more about that later in this course. But iron has, neutral iron has 26 electrons to hydrogen's 1. So there's going to be a lot more transitions for iron. And so these represent all the different energies between certain energy levels. But what the atomic spectra really tell us is that the electrons in an atom can only have certain energies. So I'll show you sort of an example of this very simply kind of with hydrogen, where if we have a energy diagram, and we could have certain energy levels. We could have this energy level, this one, this one, this one, this one. Okay, so a bunch of different energy levels. These are the only allowed energies that the electron can have, and they'll go on, but just simply we'll do this. Well, then there are certain energies that light can have as it transitions. Right? You can have these energies of light, the amount of energy that is emitted when you go from this level to this level, here to here, here to here, here to here. You could also have this transition, right? Or you could have this one, that one, or that one, right? So there's a bunch of different ones, but in general, these are very specific, right? There's not a continuous amount of transitions you can have. There's only certain energy levels, and so certain transitions, certain energies, right? Because the energy of the light that's released is the difference between the energy level. It's how much energy the electron loses from going from here to here, right? So hopefully that makes sense. That's where these energy levels come from. And that is why we see only certain lines and certain spectral lines, because the electron can't just have any energy and drop down to any energy. There are certain energy transitions that the electron is allowed to make by quantum mechanics. Right? So what this tells us is that energy is quantized, that there are only certain energies that electrons are allowed to have. That's a really important point. Okay? So hopefully this makes sense, and I'll see you in the next video.